Let's take a look at a couple examples of work that is caused by a force. Alright, so the first one we're going to look at is weight. If we just start out looking at our old free body diagrams, if we have an object in space, it just has some mg pointed down. Well, let's go ahead and make a coordinate system and show you why only the y direction matters. So here's y, x, and z, and let's give us a path. Let's say we took this from somewhere on the ground, maybe up through space, and this is some mass. Alright, well, this goes from some R1 to some R2 and has this weight component pointed down. We can also call this W. On this path, it's going to be traveling tangent to the path, undergoing infinitesimal displacements dr, getting from R1 to R2. So if we want to find the work from 1 to 2, we found that we can integrate f dotted into dr. Well, what is f first? Well, that's our force, and in this case, it's a minus mg. Let's call that a negative mg in the j direction. Alright, now what about a position vector? This has some x, y, and j components. So if we did the work from 1 to 2, we need to consider that we have the minus mg in the j direction, but it went through some displacement. Some dx in the I direction, some dy in the j direction, some dz in the k direction. And these are dotted. So both of those are vectors. And what we notice is that the only components that matter are these j components, because when you take the dot product, only like components multiply together, the rest turn to 0. So j times j is equal to 1, so we get a 1. We have a minus mg from right here, and a dy. So we can say the work from 1 to 2, I guess I should have labeled the 1 to 2, is not dependent upon the x or z motion at all, only the motion in the y direction. So we have a negative mg delta y. And you may see this as a minus w delta y. I just like the mg. So with gravity, only the y component matters, or displacement. And that is because that is the component in line with the gravitational force. Okay, let's take a look at the work of a spring force now. Alright, so we could have some spring on a mast, right? It could be pushing either direction depending on its initial displacement. We know we can start with du is equal to we're going to put a minus in because of x in the opposite direction, minus ks ds. And I'll show you where this came from. So the spring force is equal to the spring constant times delta S. So that is not a subscript S, that is a function of position S. Alright, now let's say that work from 1 to 2 is equal to the integral of this. The k is a constant and can come out, and then we get s squared over 2. We need to evaluate from s2 to s1. And we get the work, or u, from 1 to 2. That's minus 1/2 k delta x. I'll talk a little bit about the sign as we do some examples. It'll make more sense, but I'll make a table for you right now. And honestly, if we have a spring problem, unless it specifically asks for the work, I wouldn't probably use work energy method. I would probably use the conservation of energy, which is my favorite of all, and it simplifies things down greatly, and I'll show you quite a few tips and tricks on how to really utilize the conservation of energy to work even work energy theorem problems. It's all the same stuff, so I feel like I understand it better in work energy, or sorry, conservation of energy, and I feel like I can make it make more sense for y'all. But if we make a table with the direction of displacement, and the direction of the spring force, and whether the work is positive or negative. If the direction of displacement is the same as the spring force, the same direction, then it does positive work. If they have opposite sense, then it's negative work. So if I'm pushing on a spring, compressing this thing, the spring force is pushing back on us this way. The displacement, however, is to the left, and we're going to be having an opposite sense, and it's doing negative work. If the spring was extending because it was compressed and making this move out rapidly, the spring is doing positive work on the mass because it's changing that spring energy into kinetic energy. Alright, thank you. We'll see that we can treat similarly to the spring force and the work of a spring force friction. They're always in the same. It's actually almost easier because it's always in the direction of displacement, except in the opposite direction. But if that makes sense, we have something with a frictional force this, as long as this doesn't get lifted off the ground, the motion would be in the exact opposite direction. So the minus sign comes out easily there. And we don't have to worry about any angles theta.